Hello there and welcome to Pressure and Wind. This is part 1. There's a second lecture which is part 2. Everything about pressure and wind is in chapter 5 of your textbook. Specifically today we're dealing with pages 97 to 103. Right? And we have sort of 6 topics for today. We have air pressure, we have the basic wind story, and then we're going to go into detail and talk about the 3 forces that we have to account for when we talk about wind. And then finally we'll bring it all together. And this lecture is in 3 parts. So you have 3 separate videos. You also have a handout for the Coriolis force. And you also have a worksheet that you can work on and fill out. Okay, so let's get started. What we're essentially trying to do is take our normal weather map that we've been looking at and the information that we have on this weather map, and from the weather map figure out what's going on with wind speed and wind direction. So this is a map, for example, where the arrows show you the wind speed and the wind direction. And all the information you need to construct a map of wind speed and wind direction is contained in this basic weather map. Because that map shows you the location of the high pressure areas, the location of the low pressure areas, and it shows you the isobars, here these white lines. And all you need to know to predict wind speed and wind direction is the location of the high pressure areas, the location of the low pressure areas, and the location of the isobars. So let's look into this in detail. First of all, air pressure variations, the difference between areas of high pressure and areas of low pressure. Well, air pressure, of course, as we talked about, is greatest at sea level and decreases as you go up. And you can think about it as sort of the weight of the atmosphere, if you will. Right? How much does the atmosphere weigh? If you think about each air molecule, each nitrogen, each oxygen molecule has having a weight, then you can sort of think about it that these things settle down towards the surface. Right? And so closer to the surface, you just simply have more air molecules. That gives you greater air pressure. Right? So that being said, it turns out that air pressure varies spatially. Anytime on the planet, on average, yes, the average air pressure is measured in millibars, and the average air pressure is 1,013 millibars at sea level. But anytime you look outside, anytime you look at the weather map, you'll find areas where the pressure is high and areas where the pressure is low. That's just the way it is. Air pressure is never constant across space. And if you travel across the country, you travel across the region, you travel across the world, air pressure will always change. There's always areas of high pressure. And you can think about areas of high pressure as mountains of air, piles of air, if you will. And low pressure areas you can sort of envision as areas of lack of air or holes of air, if you will. Right? So let's see what happens if we play this out. An air pressure high, for example, you can imagine here as a big pile of air, if you will. And low pressure is an area where there's less air. And what happens is that air always tries to move from areas of high pressure down the pressure gradient to areas of low pressure. And that's fundamentally what gives us wind. So the fact that we have areas of high pressure and areas of low pressure gives us a pressure gradient. And air always wants to flow down the pressure gradient from the highs to the lows. So that's the first step in trying to figure out what the wind does, is look for the high pressure areas, look for the low pressure areas. So here's a simplified air pressure map of the United States. Right? The black lines are the isobars, which are isolines of equal air pressure. Right? This is page 99 of figure 5-4 in your book. And we get these isobars, and they're created from point measurements. Right? And you can see the horizontal patterns of air pressure. In this particular case, we have a high pressure here, and we have a low pressure here in the southeast of the country. Right? Low pressure area, high pressure area. Right? It's a schematic. Right? So how do we get low pressure areas. We'll talk about that more next week, but basically what happens in low pressure areas is that somehow air is rising. And as the air is rising up, you can think about it as leaving sort of a gap of air molecules behind near the surface. And that usually gives you wet and stormy weather. Right? Now, how do we get a high pressure area? A high pressure area we get by sinking and by contracting air. When air is sinking down, basically creating a pile of air, if you will, creating a pile of air molecules near the surface, that gives us high pressure, and high pressure means dry and stable weather. But what we're interested here is not so much the weather. We are interested in this concept of pressure differences, and how that relates to wind. Right? So, on average, yes, the higher you go in the atmosphere, the lower the air pressure gets. And yes, on average, the average air pressure at sea level is 1,013 millibars. However, you will always have these areas of high pressure and these areas of low pressure on the surface of the Earth. So, for example, on this weather map, we have low pressure, low pressure, low pressure, high pressure here, and high pressure here. And these high pressure areas, these highs and these lows, those give us the wind, because without these pressure differences, there would be no wind. The other thing you can see from a weather map is the spacing of the isobars. So, for example, right here, see these white lines? These are the isobars, and they're spaced, they're packed very tightly together. That means we have a strong or a steep pressure gradient, and we have very fast winds. Conversely, out here, you have a big spacing between the isobars. Right? Pressure gradient is rather flat, and the winds are rather weak. Another example here. So any weather map you look at, you will see high pressure areas and low pressure areas. And here we have a bunch of highs shown in blue, and we have a bunch of lows shown in red, right? And because we have these differences in pressure, low pressure area here, for example, high pressure area here, for example, that gives us a pressure difference, and that gives us wind speed. All right? So that's the basic story of, oh, here's another example. Here we have high pressure over the middle part of the country, high pressure here over Texas, and areas of low pressure here over New England, right? And then you can see how tightly these isobars are spaced. What does that mean? That means there's pretty high wind speed in this part of the country. Why? Because the isobars are close together, which makes a very steep pressure gradient. Anyway, you can think about as a high pressure area as a mountain, and as a low pressure area as a hole, and the air just rushes from the mountain into the hole down the pressure gradient. The wind blows from the high pressure area to the low pressure area. That's the basic situation. It gets a little bit more complicated than that, but the basic fact remains. Now, let's talk about the wind story, because wind is two things, right? Wind speed and wind direction. And we measure that with these gizmos here. Here's our weather station on the glacier on Kilimanjaro, and up here we have our wind sensor with basically a propeller, or rather an impeller, if you will, measures the speed of the wind, and then you have a wind vane basically that adjusts itself to the wind direction to give you wind direction. So wind, by definition, there you have it, is the horizontal movement of air relative to the Earth's surface. And in physics, we call that a vector. That means it has a magnitude. Wind has a magnitude. That's the wind speed. And it also has a direction. Where does the wind come from? Right? So a vector always has a magnitude and a direction. In general, right? Here's the gray box. Wind always blows from highs to lows. Wind always blows from areas of high pressure to areas of low pressure. The greater the pressure difference, the faster the wind. That's what we call the pressure gradient force. We will get into that in just a minute. That's the general situation. Unfortunately, there's more to it. unfortunately, there's more that we have to deal with. Because there's two additional forces we have to account for. The Coriolis force and the friction force. Right? So wind speed and direction are influenced by the pressure gradient force, the Coriolis force, and the friction force. And we need to think about all three of them if we want to forecast wind speed and wind direction. We have to consider the pressure gradient force, we have to consider the Coriolis force, and we have to consider the friction force. And that's what we'll do in the next part of this online lecture. Part 3 will be, section 3 rather, will be the pressure gradient force, section 4 will be the Coriolis force, and section 5 will be the friction force. And then we'll put it all together. So that's what we're doing. Okay? So we'll see you in the next part where we'll talk about these three forces.